This is again Ma'am Vici. Our previous discussions focused on the basic concepts of fluid flow phenomena. We also did the calculation of the Reynolds number on the succeeding video. So today we will discuss dimensional analysis in fluid flow. Well. Before anything else, have you subscribed to my channel already? If you haven't, it is never too late to hit the subscribe button. Okay, what is really dimensional analysis? Hmm. It is a mathematical technique. I like to refer this technique as the play of units because it is easier to understand than the technical term dimensional analysis. It is also easier for an engineering student to understand the principle of consistency of units. That is, each term in the equation must have the same dimension. We take note also the dimensional analysis. In it, we group the variables into the dimensionless parameters, thus reducing the number of initial variables. Dimensions of the physical quantities may be expressed in terms of fundamentals like mass, length, time, and sometimes temperature and thermal energy. Because problems in fluid dynamics and heat transfer have many parameters, dimensional analysis reduces the number of variables, making the analysis less difficult. The table shows the important variables in momentum transfer. On the left side are the variables. In the middle are the symbols of each variable that are generally recognizable by chemical engineering students. In the right side are the dimensions of each variable. This table shows the common dimensionless parameters in momentum transfer, like the Reynolds number, Euler's number, coefficient of skin friction, fluid number, Weber number, and Mach number. Now let us look into the situation in the problem. Consider the pressure difference, change of P, between 2 points of a pipe where the fluid is flowing as a function of the pipe diameter D, pipe length L, fluid velocity V, the fluid density rho, and the fluid viscosity mu. We start with interpreting the situation in the figure. The relationships in the problem can therefore be expressed as change of P is equal to the function of T, L, V, rho, and mu. This is given, of course, in the problem. The form of the function is unknown, but we can expand it as a power series. Thus, change of P is equals to the constant of T raised to n1, L raised to n2, V raised to n3, rho raised to n4, and mu raised to n5. The requirement of dimensional consistency is that the combined term on the right-hand side will have the same dimension as that on the left. Since the term on the left is pressure, then all the terms on the right must have the dimensions of pressure. That is where we need to express each variable in the equation in terms of mass, length, and, of course, time. We call from the table that change of P equals m over L T squared, or we can write that as m L raised to negative 1 T raised to negative 2. And V is equal to L over T, or again, that is L times T raised to negative 1. Rho is equivalent to M over L cubed, or we can have that again as M times L raised to negative 3, while mu is equivalent to M over LT, or again, M L raised to negative 1 and T raised to negative 1. Then substitute the dimensions of the equations. Thus, change of P is substituted. Also, you have your D, you substitute that. And then we have also our L, which is equivalent to the big L. We substitute that. Then we have V, which is equivalent to L times T raised to negative 1. And then rho, which is equivalent to M L raised to negative 3. And mu, which is equivalent to M L raised to negative 1 and T raised to negative 1. Meet the conditions of dimensional consistency. The fundamentals of M, L, and T must be equal to the indices of each of these variables. Thus, for N, on the left is mathematically understood to have an index of 1, but on the right, we have an M which has an index of N4, and also we have an index of N5. Also, for N, on the left, it has a negative 1. On the right, there is an N1, an N2, a 1, of course, that is understood to be positive N3. And then we have a negative 3 and 4, and we have a negative N5. T on the left has also a negative 2, but on the right, you have a negative N3 and a negative N5. We will then simplify the equations. From M, which is 1 equals N4 plus N5, we can have that as N4 equals 1 minus N5. From T, we have a negative 2 equals negative N3 minus N5. We can also have that as N3 equals 2 minus N5. These two equations that we derive from M and T will be substituted in the equation of L. Of course, you can have your own algebraic simplifications, whatever mathematical manipulation is convenient to you, so long as you do not violate any mathematical principle. The equation for L is negative 1 equals N1 plus N2 plus N3 minus 3 N4 minus N5. Recall that the equation that we derive are N3 is equals to 2 minus N5 and N4 equals 1 minus N5. We can substitute equations of N3. And then also we substitute the equations of N4. And then we simplify the equation. We get therefore 0 is equals to N1 plus N2 plus N5. Or in terms of N1, the equation becomes N1 equals negative N2 minus N5. Now we are able to derive three equations. Recall that we also have the equations of change of P. So we substitute the equation of N4, then the equation of N3, then the equation of N1. The result is, of course, change of P is equals to the constant of D raised to negative N2 negative N5 L raised to N2 V raised to 2 minus N5 rho raised to 1 minus N5 and mu raised to N5. We will then simplify again. For D raised to N2 minus N5, we will be getting 1 over dN2 times 1 over dN5. While L raised to N2, we still have an L raised to N2. For V raised to 2 minus N5, we will be getting V squared times 1 over Vn5. And then for rho raised to 1 minus n5, we will have rho times 1 over rho raised to n5. While, of course, your viscosity raised to n5 is still viscosity raised to n5. And we group together the terms with similar coefficients with the end goal of making the groups of, the groups dimensionless. So we have for those who are on in N2, you will have that in one term. For those that has N5, you are also having that in one term. Simplifying further, take note that V square and density, which is in the middle of among the terms on the right side, does not belong to any group. So we have only terms raised to N2 and raised to N5. Take note also that the right side of the equation has two units of pressure. So we cross multiply your V square and rho to the right side so that all the terms now are consistently dimensionless in terms of units. Now we know that the equation for the Reynolds number is d times v times rho over mu. So if we convert the term to its inverse form, we will be having dv rho times mu, over mu raised to negative n5. We can write the resulting equation into change of P over density V square equals to the function of L over D and dV density over mu. Notice that we are able to reduce the original equation with 6 variables to 3-dimensionless groups. However, the solution, of course, will depend on how you solve the simultaneous equation. In this case, if you solve the equation in terms of other variables, like you use N3 and N4, it will result in different dimensionless groups. That should be something for you to work on after watching this video. Thanks to you. There will be a follow-up video on dimensional analysis, and that would be on the Buckingham method of dimensional analysis. Thank you so much.